Alright, on this video we're actually going to take a look at two different modules. They kind of go together, but we're going to start out with 4.2, sorting out the change. So in this, they give us a bunch of different types of patterns, and they want us to sort them. These relations into three different categories, and here's the categories we're talking about. Okay, so the first one is neither. Well, I guess that's the last one, meaning it doesn't follow the first two. So the first one, equal differences over equal intervals. Okay, well, let's break this down. First of all, equal differences. What does that mean? Okay, what type of pattern are we dealing with that has a constant difference? Okay, that word difference deals with addition and subtraction. So these are the arithmetic types. Okay, so it means that pattern on the outputs would be the same. We're adding or subtracting by the same number. Okay. Now, the second part, over equal intervals. An interval is just a section of space or time. Okay. So on this part, equal differences is the output, whereas equal intervals is the input. Do I have equal space in between? And look on this side. So number one's a good example of that equal differences over equal intervals. Because on this, checking the x, do we have equal intervals? Well, yeah, we're adding 5 each time, right? There's an interval of 5 between each of these numbers on the input. So we've got equal intervals, but do we have equal differences? We'll check out the output. We're adding 10 each time on the output. So equal intervals and equal differences. So equal differences over equal intervals. So, and we know that's an arithmetic pattern, so type of pattern of change, we would say the equal differences. And you can just abbreviate that equal diff. Okay. How did we find that pattern of change? Well, we looked at the patterns in the inputs and outputs. Okay. So that's what it would be like to be equal differences over equal intervals. Okay. Now, if we're talking about the equal factors over equal intervals, that equal intervals is the same idea. It's still the input. Now, equal factors mean multiplication. So this one here, we're dealing with the geometric pattern, right? Which would be multiplying and dividing. Okay, so we're looking at, once again, we check the inputs. Are the intervals equal? And then we look at the factors. Are we using the same factor each time? And if it doesn't follow either of those, that's why we have the neither. Okay, so this is what we're kind of looking for: equal differences or equal factors, and we're trying to decide how we can find that pattern out. And if it's not, we call it neither. Okay, so let's take a look at number 2. Now, number 2 looks like it's in that recursive form, right? But a little different than we're used to. Okay, so we've got f of 0 equals -3. Then they go f of n plus 1 equals 5 divided by 3 times f of n. So here they've just went plus 1 instead of minus 1. So this is actually to get the next term, and f of n would be the current term. Okay? So kind of just thinking ahead. So we take the current term and we multiply it by 5/3 to get the next term. And we start at -3. So it may be a good idea to make a table. Here's your input, here's your output, just to get an idea of what's happening here. So if we look at this, we're multiplying by 5/3. Okay. So if we multiply -3 by 5/3, we get -5. If we times -5 by 5/3, we get -25/3. Okay. And if we keep going, we're going to get ever-increasing fractions. 5 times 25 would be 125. 3 times 3 would be 9. Okay. So it's growing quite a bit, right? And it's growing by a factor. So we made some equal intervals, right? We're adding 1 on the input each time, so we have equal intervals, and we're times them by 5/3 each time. So this would be equal factors because we're multiplying. Okay, you could have found the pattern by making the table or by noticing this part, right? That we're going from to the next from the current, and we're adding 1 each time. And so, I'd say looking at the recursive equation and seeing a factor. Get at 5/3, we're multiplying by it. Alright, number 5, we look at this one, and what does this look like? Well, we got y equals a times x minus 3. So, what are we doing here on this pattern? Well, we're starting at -3, right? So we'd start at -3, and what are we adding? We should recognize that a times x, that's like a plus a plus a plus a. Right? So we're adding the same difference. That's an equal difference. Okay, and we're doing it for every x. So if I do it for 1x, I add a once. If I do it for 2, I add a twice. If I do it for 3, I add it 3 times. So our intervals are going up by 1. So what type of pattern of change? We've got equal differences. Do we have equal intervals? Yeah, right here. That kind of stands for the intervals. So how did I find the pattern of change? If I recognize that a times x is arithmetic, that a times x, we're just multiplying, we're adding a multiple times. Alright, number 3 and 4 both deal with this pattern up here. So the first one, 3, wants us to do the perimeter. So on step 1 it'd be 1, 2, 3, 4. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and you get the gist, right? So if I look at this one, okay, we can see that we are adding 6 each time to the perimeter, right? So we have a equal difference. Now is it an over an equal interval? Well, step 1, step 2, step 3, step 4, I'm adding 1 step each time, so it's an equal interval. So that's an equal difference. So how did we find the pattern of change? Counting perimeter and seeing plus 6 each step. That equal interval, equal difference over equal interval. Okay. So there's 3. So now I'm going to erase a bit. And now we're going to look at 4, the pattern of change of the area of the figures. Okay. So the area would be like this 1 square would be an area of 1. This would be an area of 4 squares. Okay. So we're just basically counting the squares for the area. And if you don't believe me, like this would be 9, I could take these 3 and move them over here. I'd have 1, 2, 3, 1, 2, 3, 3 times 3 is 9. So it works out that way. Okay, now if we're looking at these ones, we'd add 3, then add 5, then add 7. Okay, is that equal differences? No. Is there a way to get equal factors out of that? Well, that'd be times 4. That would not be, that wouldn't work either. So it's not equal factors, it's not equal differences, so it's going to be a neither. Okay, there is actually a pattern. It's like 1 squared, 2 squared, 3 squared, 4 squared. That's the pattern you're going. But it's not a pattern we're familiar with yet. Next year you will be. So this is a neither. How did we find it? Counted boxes. Because it is over the same intervals, it's just a different type of pattern than we're used to. Alright, if we look at number 6, okay, this one, do we have an equal interval? Yes, we're adding 5 each time on the input. Do we have an equal difference or factor? Well, we could say we're adding 0. I suppose that would be an equal difference. We could also say we're multiplying by 1. So since it fits both, I would probably call this one neither, because it's something different going on here. How did we find the pattern? We checked our inputs and outputs. Okay, because it could be both, you could argue that it's one or the other, but to me, since it can be both, it's got to be neither, because there shouldn't be able to be both. Something else is going on. Okay. Okay, looking at 7. The height from the ground of a person on a Ferris wheel that is rotating at a constant speed. So it's probably helped to draw a picture. So you got a Ferris wheel here, right? Okay, you've got a person sitting right there. And as time goes along, they're getting further and further and further away from the ground, right? And they get to this point, and they're the highest they're going to be. Then as it keeps moving, they're getting lower and lower and lower until they get to the ground. Okay, so if I were to graph this, which I think will help to understand, we start out here, we'll say, we're at this height, right? And as time keeps going, we'll say this is when we hit the top of the Ferris wheel. I'm going up, 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 up. Then I stop. Then we start going down, so we're getting closer to the ground, so it's coming down. Okay, so it would look like that. Okay, so we're adding the same amount of distance until we get up to the top. And actually, we're not really adding the same amount of distance, because over here it'll probably add a little bit quicker than right here. But here we'd be subtracting. So this one's a neither. How do we find the pattern of change? Looking at picture/graph. Okay, number 8, y equals x. Okay, well this one is actually in that slope-intercept form. It's just this would be plus 0, and that would be 1. So 1 times x means we're adding 1 each time, right? So that's going to be an equal difference. How did we figure this out? Recognize that slope-intercept form, which is arithmetic. And we should notice that these arithmetic patterns are giving us equal differences over equal intervals. Alright, number 9. So let's take a look at this one. So our inputs. Well, we're adding 4, then we subtract 8, then we add 12, then subtract 16. Okay. So, is there a way to think, well, we can't multiply because of the 0. So are these equal intervals? They're not equal intervals. So this is going to be a neither. How did we find the pattern? We found that no equal intervals were happening. And then even over here we add 3, subtract 5, add 9, subtract 12. So it's kind of all over the place, isn't it? Alright, number 10. The algae population in a pond increases by 3% each year until it depletes its food supply and then maintains a constant population. So I think, graphing this one would be a good idea. So increasing by 3% would mean we're multiplying by 1.03, or 103%. Because they were taking the population, we're adding 3% to it. So then we're multiplying our population by 103%, or 1.03, until we get to the food supply, and then it's just going to stay the same. So it's going to start here and go up, 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 and then it's going to kind of just level off, isn't it, once it hits that peak. So at the beginning, when we're still growing each year, equal interval, equal factor. So you could have said equal factors. However, and that would have worked. However, because it's going to maintain that population, we're going to have to call this one neither. Okay, how do we find the pattern? By thinking of the graph. Now looking at number 11. So we look at this pattern. So check to see if we have equal intervals. And we do. We're adding 1 each time. So what are we doing on this side? First we may want to say we're subtracting, but 238 subtract 76 is bigger than 100, which 76 minus 22 is less than 100, right? So we may want to see if we are dividing by a number. But first let's just try this subtraction. So we subtracted 162, then 54, then 18, then 6, and then 2. So there is actually a pattern here. It's probably tough to see. You may have to go out a little further and do the same thing, but you probably won't notice it. The pattern here is 2 times 3 gives me 6. 6 times 3 gives me 18. 18 times 3 gives me 54. 54 times 3, okay? That's what we have going on here. And if I try to divide them, I'm not really coming up with the same number. So here's the pattern. So is that one we're familiar with? That's not equal intervals, that's not equal factors, or equal differences. The differences are different. They're all factored a little bit, but not the way that we need it to be. And I think I just spelled neither wrong, didn't I? Okay. How we found this pattern of change? Well, we just looked at inputs and outputs. All right. So on number 12, I kind of cut off part of it, but I believe it's just you take a ball and you drop it from a height of 8 feet. So it's up here at 8 feet, and then you drop it, and then the ball bounces to 80% of its previous height each time. Okay. So kind of like that. Alright, well, we're dealing with percents here, and percent should key us into the fact that we're going to be multiplying here. We're saying if it bounced the same height we dropped it, that would be 100%. But it's going to 80%. Okay? So what we would do is we'd multiply by that 80. So each time we're timesing by 80, which, depending on when each bounce would be an equal interval, and we're multiplying by an equal factor, so it would be equal factors. Okay, how did we find the pattern? Just thinking through what it meant. Okay? Okay, now the last one on this part. Okay, do we have equal intervals here? I mean, I guess you could say an interval of 0, and then our y value is, do we have equal factors? 5 to 10. I mean, let's try reordering these. Negative 20, negative 10, negative 5, 15, 35, 50. I'm not seeing an equal factor. Okay, this would be divided by 2. This would be divided by 2, but then you'd have to times by negative 3, so not equal factors. If we subtracted them, minus 10, minus 5, plus 20, see, so it's neither. How we looked at outputs and inputs, but I'd probably call it neither based off of that to begin with. Okay. Alright, so that was 4.2. That's all we needed to do on 4.2. Now 4.3, it wants you to just choose 2 problems from the linear, which was that equal differences, and 2 from exponential, equal factors. Okay, to try to make as many representations, so as many models as we can. Okay, so we can rule out 13. We can't do 13, right? So let's go like this. I'm going to kind of work my way backwards. Okay, so we took the ball, so graphing this, I think that would be a good way to think through it. So we would probably use time here as our x-axis, and then the height as our y. Well, we start up here, okay, and then we would drop it, so it would be at this height, and then like at the first interval of time, maybe a second, 2 seconds, however it would say, okay, Maybe we should make a table first. That might be better. Time and height. So we'll say at 0, what should we start out as? Maybe, 8 feet, right? We started out at 8 feet. Okay, so then we're going to multiply 8 by 0.8, or 0.80%, timesing by 0.80, which would give us 6.4. So we'd 1, 2, 3, 4, 5, 6, 7, 8. So 6.4 be somewhere about right there. Then at 2 seconds, 6.4 times 0.8 gives us 5.12. So we'd go to 5.12. Then the 3 be 4.096. Then it would be 3.2768. Then 2.62144. 2.097, 1.677, 4, 5, 6, 7. So 4 would be a little above 3, then about 2.5, then about 2, then about 1.6. So you see it's kind of got that curved going down. So there's our graph. There's a table. We kind of drew a picture of it to begin with, something bouncing like this. Okay. Now, a recursive equation. Well, where did we start? So f of 0 was equal to 8. Then what did we do? Well, to get f of n, we went f of n minus 1 times 0.8. So our explicit, what would that look like? It would be f of x, or n, or t. Yeah, let's use t for time. F of t equals, we started at 8, we multiplied by 0.8 to the t. Okay? There's all the representations I can think of to do here. Okay, let's take a look at these ones. So we've got another, well, it's technically a neither. Maybe we'll come back to 10. Okay, 9 is neither. Equal differences, number 8. Okay? So let's go like this. So this one would be easy to make a table, right? X and Y. So if we start out at 0, if X is 0, what is Y going to equal? 0. They're equal to each other, so basically it's going to look like this, isn't it? So for an equation, we've already got one equation. Okay. We could graph it easily. Just basically like this. Straight line, right? It keeps going. Okay, could we decide if it's discrete or continuous? Yeah, we could. This one would be continuous because if I put in 1.5, we'd get, for x, we'd get 1.5 for y. Okay, could we come up with a story problem? Yeah. Every day I ate one pizza. Now, how many pizzas did I eat? Could we make a recursive equation? Yeah. F of 0 would equal 0. F of x would equal f of x minus 1. And then this is grown by adding 1, so plus 1. Okay. Anything else? I guess we could draw a picture of yourself eating pizza every day. Something like that if you wanted to. But you don't necessarily have to. Okay, so we've got one of each. This one we called neither. Okay. This one, number 3, was a good one. We've got a picture. If we made a table out of it, we have our steps, we have the perimeter. So at 0 we had 4. At 1 we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so we were adding 6 each time, right? So we're adding 6 each time, so we could go y equals, our starting number was 4, plus 6 multiple times. If we were to make an equation, the explicit recursive would be f of 0 equals 4, f of x equals f of x minus 1, plus 6. Okay, could we try to make up a story problem? Yeah, somebody in building fences or something like that, making tiles, finding a perimeter, something like that. Could we graph it? Yeah, easily. 0, 4, 110, and so on. Okay, and this one maybe you could make discrete. Okay, instead. Something like that. Okay, so we got our two equal differences, our two linears. Okay, how would we do number 5? Well, with that A there, that would be kind of tough to deal with, so don't worry about that one. Let's take a look at number 2. Okay, so number 2 and number 1 kind of seem to be the ones that we can still use, right? So if we looked at number 2, we've got the recursive. So as a table, what would it look like? Well, 0 is -3, then 1, then 2, then 3. Okay, then we're multiplying by 5/3, so that'd be -5, right? Yep. Now you may want to leave it as a fraction, you may want to do it as a decimal, either one works. And we'd have -8 1/3, -13.8, because I don't know what 0.8 is, and so on. -23.148. Okay, that would be like -8.3. Okay, so our explicit equation would be y equals -3 times 5/3 to the x, because it's that exponential. If we graphed it, right, 1, 2, 3, 0, -3, 1, -5, so we're going down. So I should have drawn my graph differently. More like that. So that's -13. That's 3. So it'd go down something weird like that, huh? So it's still kind of got that curve, but kind of opposite from what we're used to seeing, because of that negative. Throws it off. Okay, you could try to come up with a story on this one. That would be kind of tough, since you keep losing something, going into the negatives. Maybe you have a gambling habit, and every day you're losing 5/3 of your money, something like that. I think that's probably good enough. Okay, this last one, we'll take a look at this last one in the remaining time. Okay, once again, we've got the a table. So if we graph this, well, that's some big numbers in the negative, right? So we'd be going down. 0, we'd end up at 3 somewhere, so it'd be going down something like this. And I'm not being too specific for sake of time, because I'm almost out of time. So it would look something like that, where this would be down really low. Okay. Then the recursive would be f of 0 equals 3, and f of x equals f of x minus 1, and I believe we were adding 10 each time, plus 10. Explicit would be f of x equals, we started at 3, and we're adding 10 each time. So something like that. You could come up with a story problem. 30 days ago, that'd be tough with the negatives. Maybe like 30 days ago I owed somebody $57. Today I finally, made it all up and actually gave him some extra $3, something like that, and I earned $10 every 5 days to pay him back, something like that. So anyway, there we go. We're pretty good at making those models, so not too worried about that. But there we go for 4.2 and 4.3, taking care of both of them.